Hello everyone. Today let us discuss the topic Wheatstone Bridge. Frequently asked question, that is the derivation for the board exam. And based on this we have so many applications. Further we have the topics meter bridge and also potentiometer, which are based on this Wheatstone Bridge. And we have to solve so many networks, that is problems, numerical problems based on this Wheatstone Bridge. So without wasting much time, let's start our discussion. So what is this Wheatstone Bridge? Okay, so let's go. So this is a Wheatstone Bridge which I have drawn here. It contains 4 arms. A bridge means generally a connection between two places. Similarly, this is a Wheatstone Bridge which is connecting so many branches here. So arms, we call them as arms. Here we call them as arms. Which are arms? AB is a arm, BC is a arm, CD is a arm, DA is a arm. Like that, AC is also another arm, BD is also another arm. So these are the so many arms, that means connections. And already I told you in my previous video that is a dot is a junction and a loop is a closed circuit. So what we will analyze now, junctions and loops, using Kirchhoffs 2 rules, that is KCL and KVL, Kirchhoffs current law and the Kirchhoffs voltage law. We will apply them to this network. Now before going, in the arm AB we have the resistance R2. In the arm BC we have the resistance R4. In the arm CD we have the resistance R3. In the arm DA we have the resistance R1. In the arm AC, that is AC, we have taken the battery with the EMF E. And in the arm BD we have taken the galvanometer G, that is galvanometer. So this is the circuit connection. AB has the resistance R2, BC has R4, CD has R3, DA has R1, AC has battery, BD has galvanometer. What is the galvanometer? A current sensitive device. That means just like a meter. The speedometer, or the different meters, they measure different things. To measure the speed we have 1 meter. To measure the current we have ammeter. To measure the volt, that is voltage, we have the voltmeter. So like that we have so many meters. Then in the same way to measure current, or to know the presence of current, we use a meter called as galvanometer. So galvanometer is connected between the ends B and D. So the BD is called as the galvanometer arm. BD is called as the galvanometer arm. Between the A and C we have connected the battery. So AC is called the battery arm. AC is called as the battery arm. And BD is called as the galvanometer arm. So with this introduction, let us further continue our discussion. This is a very, very, very important derivation. We have 4 resistors, R1, R2, R3, R4. Each across two junctions, A, B, B, C, CD and DA. And also we have across AC a battery, that is called as the battery arm. We call it as the battery arm. And across BD we have taken the galvanometer. So BD is called as the galvanometer arm. Let us see. For simplicity, we assume the cell has no internal resistance. Battery has no resistance. Let us assume battery has no resistance. So in general, there will be so many currents flowing across the resistors, and currents are also flowing current is also flowing across the galvanometer, that is through the galvanometer. So many currents will be flowing in a network. In the present network also, currents will be flowing across this network like I1, I2, I3, I4. Similarly, current through the galvanometer is denoted by I subscript G. Ig is the current flowing through the galvanometer. Okay, let's go back to the picture once again and see. So here Ig is the current flowing through the galvanometer. Suppose if Ig is equal to 0, that is current through the galvanometer is 0, then it is a very important point to be noted here. We say that the bridge is balanced. When the bridge is balanced, when the current through the galvanometer is 0, that is when Ig is equal to 0, we say that the bridge is balanced. Now, let us apply the Kirchhoffs junction rule, the KCL, to the junction D. D means the point which I am circling here. At this point, you can see I1 is flowing inside, Ig is flowing inside, I3 is flowing outside. That means I1 and Ig are taken as positive and I3 is taken as negative. Sum of the currents meeting at a junction is 0, that is KCL. I1 plus Ig minus I3 algebraic sum is equal to 0. I1 and Ig are positive because they are flowing towards the junction. I3 is negative because it is flowing away from the junction. Therefore, I1 plus Ig minus I3 is equal to 0. But in the balanced condition, Ig is equal to 0. Ig is equal to 0. Therefore, I1 minus I3 is equal to 0. Therefore, I1 is equal to I3. This is equation number 1. This is equation number 1. I hope you got it. So, let us continue. Let us apply KCL, that is Kirchhoffs current law, to the junction B now. So, let us apply it to the junction B now. So, let's take the junction B here. Towards the B, I2 is flowing inside, Ig is flowing away, I4 is flowing away. Therefore, according to the convention, we have to take I2 as positive and I4 as negative, Ig also as a negative. So we have to take like this, because algebraic sum of the currents meeting at the junction B is equal to 0. But at the balanced condition, Ig is equal to 0. Therefore, I2 minus I4 is equal to 0. Therefore, I2 is equal to I4. This is equation number 2 which I have shown here. Equation number 2 which I have shown here. I2 is equal to I4. Then after that, this first law is over. Now let's apply second law of Kirchhoff, that is Kirchhoff's loop rule. We will apply to the different loops. First we will take the loop ABDA. Let us take the loop ABDA. This one, ABDA, closed network, closed loop. In this loop we don't have a battery. So the law says algebraic sum of the EMFs is equal to sum of the products of currents and resistances. So that is the second rule. So now we are going to apply Kirchhoff's second rule to the loop ABDA. In the loop ABDA, we will go clockwise. I2 R2, that is positive. Ig into resistance of the galvanometer, let us take it as G, that is also positive, clockwise direction. But I1 R1 is clearly in this direction, opposite to them, that is anti-clockwise direction. Anti-clockwise direction. So if you clearly you can see that I1 R1 is anti-clockwise direction. Therefore, you should take it as negative. So minus I1 R1 plus I2 R2, that is clockwise direction, plus Ig, and let us take the resistance of the galvanometer as G, is equal to 0. But we know Ig is equal to 0, that is already I told you balancing condition. Therefore, this equation will become, that is I2 R2, send this to the right side, it will become I1 R1. I1 R1. I2 R2 is equal to I1 R1. Therefore, let us take this and keep it to one side. This is equation number 3, which I have shown here. This is equation number 3. Okay, so let's continue further. Now let us apply KVL, Kirchhoffs Voltage Law, to the loop CBDC. So I'm taking CBDC. So once again, I'll draw along that CBDC. So this is the loop. So in this, always we are following the notation clockwise as positive, anti-clockwise as negative. You can take anything, that is your choice. So let's continue. I'm taking clockwise as positive. So I4 R4 in the clockwise direction. So we will take it as positive. There are no EMFs. Therefore, products of I4 R4 and I3 R3, sum of the products I4 R4 plus I3 R3 plus Ig into G is equal to 0, because there are no EMFs, that means no batteries in this loop. But what happens now here? I4 R4 is in the clockwise direction, so it is taken as positive. But galvanometer Ig is in the anti-clockwise direction, so we are taking as minus into resistance of the galvanometer G, and I3 R3, that is also opposite to the direction, that is anti-clockwise, so we are taking it as negative, that is equal to 0. But once again, Ig is equal to 0, therefore I4 R4 is equal to I3 R3, that is I4 R4 is equal to I3 R3. So this I have shown here, which I am marking with the blue rectangular box. This is equation number 4. Now, if you see equation number 4, once again we will see, that is I4 R4. This is equation 4. I4 R4 into G, I4 R4 minus G into 0. 0 means Ig. In fact, it was current through the galvanometer, Ig, which we made as 0. Then minus I3 R3 is equal to 0. Once again I repeat, I4 R4 minus G into 0 minus I3 R3 is equal to 0. But equation 1, I1 is equal to I3, and equation 2, I2 is equal to I4. Therefore, in place of I4 here, we will substitute I2, and in place of I3, we will substitute I1. So we are substituting equations 1 and 2 in equation 4. In place of I4, we have substituted I2 here, and in place of I3, we have substituted I1. Then this equation 4 will become I2 R4 minus I1 R3 is equal to 0. This is equation number 5. I2 R4 minus I1 R3 is equal to 0. Equation number 5. So let's go further. From equation 3 we get already, which I have shown you here. This is equation 3. From equation 3 we got I2 R2 is equal to I1 R1. So this is I2 R2, this is 0. Send it to this side, it will become I2 R2 is equal to I1 R1. So the same thing is written in the next page. That is, you can see here, from equation 3, we get I2 R2 is equal to I1 R1. Therefore, divide I1, bring this I to this side and take R1 to that side. You will get I1 by I2 is equal to R2 by R1. Equation number 6. Equation number 6. Similarly, from equation 5, let's go back to equation 5. This is equation 5. From here you will get I2 R4 is equal to I1 R3. I1 R3. So we will get, from this equation we will get, I will take you to the next page. You will get this, that is I2 R4 is equal to I1 R3. Then once again take I2 this side, R3 that side. You will get I1 by I2 is equal to R4 by R3. I1 by I2 is equal to R4 divided by R3. That is equation number 7. Now if you observe equations 6 and 7, observe equations 6 and 7. So both of them LHS, left side I1 by I2. Both are same, that is equal, I1 by I2. So what we can do, we can equate the RHS. We can equate right hand side. Therefore, equating the right hand side, you will get R2 by R1 is equal to R4 by R3. Very, 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 very important. R2 by R1 is equal to R4 by R3. This is called balancing condition. This is called the balance condition of the Wheatstone Bridge. R2 by R1 is equal to R4 by R3. When this balancing condition happens, the current through the galvanometer Ig becomes 0. When at the balancing condition, current through the galvanometer Ig is equal to 0. This is called as the balance condition. Once again I repeat, when the ratio, when you get R2 by R1 is equal to R4 by R3, R2 by R1 is equal to R4 by R3, we call it as the balancing condition. We call it as the balancing condition. R2 by R1 is equal to R4 by R3. We call it as the balancing condition. At the balancing condition, current through the galvanometer is equal to 0. So this is the derivation for the balancing condition of the Wheatstone Bridge. Suppose this can also be used, suppose if you have an unknown resistance. So this bridge can also be used to find the unknown resistance. So if you know 3 resistances, if you know the value of 3 resistors, R1, R2, R3, but you don't know what is R4. R4 you don't know. In that case, what we will do, what we are going to do, we will do one thing now. We know the balancing condition for the Wheatstone Bridge, that is current through the galvanometer is 0. Then R2 by R1 is equal to R2 by R1 is equal to R4 by R3. Therefore, what we will do, unknown resistance we will keep in the arm BC, that is at the place of R4, and all known resistances we will keep in R1, R2 and R3. Known resistances we will keep in R1, R2, R3. Unknown resistance which we want to find its value, we will keep at R4. Now what we will do, and we will try to balance the bridge by changing or adjusting the resistors R1 and R2, R1, R2 and R3, and finally we will see that current through the galvanometer is 0. When current through the galvanometer is 0, we know that R4 by R3 is equal to R2 by R1, but we want to know the value of R4. Therefore, send R3 to the right side. You will get R4 is equal to R3 into R2 by R1. So in this way, we can also find the unknown resistance. if you don't know the value of any resistance, you can also find it using this Wheatstone bridge. So Wheatstone bridge is a very important one, because based on the Wheatstone bridge we have also other topics, meter bridge and potentiometer, which are very useful, very useful. Especially with meter bridge, you will do many experiments for this present year. So finding the unknown resistance and finding the resistivity, and also you will do with the potentiometer comparing the EMFs of two cells, finding the resistance of a cell, internal resistance of a cell, like that. So many experiments you will do using meter bridge, potentiometer, but all of them are again based on the balancing condition of the Wheatstone bridge only. So this topic is very useful for theory as well as for your lab. Therefore, learn it carefully. Thank you. God bless you all. We will meet with the another video. We will in the next video. We will meet with the another topic in the next video. Until then, bye. God bless you all.